be talking about velocity and distance, and we can't have a conversation between distance and velocity without talking about time. So I think we're all familiar with distance, right? So we're going to go straight into velocity. And what does velocity mean? Today we're going to keep it simple and just talk about velocity in one direction. Imagine like in a one-dimensional sort of space where we just have velocity moving in one direction, in one dimension, something like this. For example, in the x direction. Okay, we can talk about it as a vector, but that's more advanced. So we're just gonna get familiarized with the basic idea. So we're gonna talk about velocity in one dimension, aka the x-axis, for the simplicity of this video here. So velocity, essentially how it relates to distance and time is as follows. Velocity equals the change in distance. We're going to call it delta. That's the symbol used for change in distance. Over a set period of time. So over a set period of time. Okay, so what does this mean? Imagine you have a car. I'm going to make a little car here that travels 30 miles every hour, for example. Okay, let's say that it starts here at point 0. Let's call it point 0 here. Point 0 in our x timeline. I'm sorry, in our distance. This is our distance line. Okay? Distance line. And let's say that at time 0, this is the time we start measuring, right? Our distance equals 0, okay? So our distance at our starting measuring time, which is 0, let's say it's it could be like 12 o'clock, just an arbitrary place where we want to start, where we start timing our timer. Imagine we have a timer and we started the clock here at 0. And then let's say that the car moves, and then at 1 hour, at t equals 1 hour, let's say that the car has advanced here at some point, let's say 30 miles. Let's say this is equal to 30 miles, right? So that means that the car, when we measure it at this time, which is an hour from this time, hour after, our time is 1 hour. And then our car here has advanced 30 miles, right? So that means that during this time, we can say that the velocity of the car was the change in distance, which is distance. This is our distance right here, traveled 30 miles, divided by 1 hour. 1 hour, which is our time period during this event. So basically, our velocity is equal to 30 miles per hour. And then we can elaborate a little bit more. Let's say that our car after 2 hours, t equals 2 hours. Let's say that our car traveled, I don't know, let's say another 50 miles. 50 miles from here to here. So if we do our little math, we can see that and we do our little velocity, that in the distance of 2 hours, right? Because now we're talking about this point here, where time equals 2 hours. In the distance of 2 hours, our car traveled 30 miles plus 50 miles. 30 miles plus 50 miles, which is 80 miles. So that means that our velocity has now changed for that 2 hour period, okay? For that 2 hour period, let's call it V2, and this is for V1, velocity during the first hour, and average velocity during the second hour. I say average velocity because it's the average. It pretty much sums up what happened during the 2 hours better than if we talk about velocity, different types of velocities. So pretty much it just summarizes what happens during the 2 hour period. This is a way of saying average velocity, okay? So for now, we're just gonna call it average velocity, but in reality, that's not the, it wasn't a constant velocity, but it's the average velocity. So during these 2 hours, the average velocity was 80 miles divided by 2 hours, which is 40 miles per hour, right? So that's how velocity relates to time in a very rudimentary sense, okay? Now we're gonna go over an example, a little bit more advanced example, and try to plot the following. Okay, so we have this little sketch here, and so we have a little sketch here, and this right here, our F, in this case, represents our distance. Okay, so this represents the distance traveled through a period of time right here. We could call it in the unit of hours, let's say. Let's call it a unit. Well, the units are really not that important, but we could call it hours or seconds or whatever it is, right? So this is just our T, and we're just gonna leave them dimensionless for now. I'm sorry, what I meant is unitless. So distance. So we have our distance graph here with relation to time, right? So if we go back to our equation and we try to find the velocity for each period of time, here we have 3 periods of times, right? We have the first period here, the second period, and the third period of time, okay? So we're gonna try to find the velocity for each period of time. So we can call it velocity. Let's call it for the first period of time, this one right here. Velocity 1 is going to equal to the change in distance over the change in time, right? So if we look at our little graph here, we can see that that we went from our distance in that 2 hour period, our first little block here, distance here. We're focusing on this one right now, on this part of the problem. Okay, so distance at time 2, right here, distance at time 2 minus distance at 0 over time 2, which is 2 right here, minus 0, because 0 is the initial 0, right? And then this 2 is from here, the second equation, the second number here, the second time. D2 in this case is going to be here, our distance at our second period, at a 2, let's call it at our time 2. And then D0 is the distance at our time 0. So from the graph we can observe that D2 is equal to 60, right? 60 minus D0, which in this case 0, D0 was 0, divided by time 2 minus 0. Basically our V1 is equal to 60 divided by 2, which is 30, okay? So V1, this velocity 1 represents the distance. This velocity 1 represents the velocity for this time period from 0 to 2 seconds, or 2 units of time, whatever they are. That's for V1. Now let's do V2, okay? This one right here, we call it V2, this section right here. And we can solve it in a similar manner, Let's go v2 equals distance at 4. Distance at 4 minus distance at 2, which is distance at 2 is here. And then distance is 4 is this one right here. This one right here, distance at 4. So our distance at 4 is going to be equal to 60. Okay. 60. And our distance at 2 is equal to 60 again. Because our distance at 2 is 60 right here. See? 60. 60. And divided by T4. T4 minus T2. And then we can go ahead and just find what these numbers are from here, from looking at the graph. T4 is 4 minus T2 is just 2. And we can go ahead and find that. In reality, our velocity did not change during that time. Our velocity was 0. So at during the time period V2, the velocity is equal to 0. And then during V1, velocity is equal to 30. And similarly, we can do something similar to find the velocity 3 in this segment of time, right? So now we're more familiar with this. So I'm just going to go pretty fast here. V3 equals distance at time 6 minus distance at time 4 over time 6 minus time 4 equals this is at 6 equals 0 divided by minus 60. 6 minus 4 minus 60 over 2. This is going to give us our V3 is equal to pretty much it's going to be negative 30. Okay. So now we have our velocities at velocity 1 constant equals 30, and then velocity 2 equals 0, and velocity 3 equals negative 30. So now we can plot these equations to find our little velocity graph. Let's start with this one right here, velocity graph. With respect to time, so we're going to call this velocity, and we're going to call this t for time. So now at time 0, our velocity was 0. At time 0, our velocity was 0. Let's use this right here, and right there at 0. At time 2, our velocity from this equation, so pretty much our velocity during this time right here, during this time period right here, it remained constant. And V1 equal to 30, right? So for the first 2 seconds or hours or whatever, or minutes or whatever time units they are, our velocity remained constant at 30. So we can just plot it here. From here to here, it was 30. Okay, now we can talk about at time 4. So at 4, our velocity was 0. So from here to here, our velocity was 0, right? I got this from here, from V2, right? This one right here. Our V2 during that time, velocity was 0. And then finally at time 6, our velocity was again, actually it was minus 30. So it's actually somewhere here, minus 30. Minus 30. here. Minus 30. We can talk about discontinuities later, but pretty much there's just some basic stuff that we should learn here. Right here at 30. I mean, later on we're gonna see what happens at these points right here, whether it's a continuity or discontinuity, because what happens at exactly time 2, right? That's probably a question some of you guys are having, but we can talk about that in another video. This is just some of the basics so we can understand some of the basic relationships between velocity and distance. We can solve this one real quick. Let's go to another example right here. So we're trying to plot a velocity, velocity versus time graph, right? Velocity versus time. This is velocity. Using what we have here, which is, call it distance, and this is our time. Okay, so between this time period here, between 0 and t, there was no change. So our distance did not change at all. So 0 minus 0 over t equals 0. So our velocity 1 here, we can call it v1. It's equal to 0. We can do v2. Let's do here, just a separation, v2, which is here. We'll call this v2. We'll call it 1 minus 0 over t. 2t minus 1t equals 1t. So that's 1, and then this right here equals 1 over t, right? And then we can do finally for this one, for this time period, which is over a period of, if we do 3t minus 2t for v3, essentially distance is not changed, so 1 minus 1, right? Divided by 3t minus 2t, it's going to give us 0 over t. So basically 0, right? So we can 0 v1. So at t right here, we're going to put time t, time 2t, and time 3t. So at v1, from 0 to t, right here, v1, 0 to t, our velocity is pretty much equal to 0. So it just goes straight like this. There's no velocity. It's not moving. Makes sense, right? Because the thing is not moving. Look, it didn't advance. It didn't go anywhere. So our graphical representation would be something like this. Something like this, where this one represents velocity equal to 0, and then for v2, which represents this section right here from here to here, we're gonna have 1 over t. So 1 over t, but essentially something like this. 1 over t right here, 1 over t. This represents our velocity during this time. And then furthermore, for the third section, we're going to, again, it's again 0 because nothing happens. It doesn't move anymore. So it's going to go from here to here at 0. And that sums up like the basic relationship between velocity and distance. This is something we can elaborate on in more detail later, but for now, this is just a basic understanding of velocity versus distance. Pretty much, to sum it up, velocity equals the change in distance over change in time, or over over a period of time. That's basically what velocity means. Thank you.